Hey everyone, good afternoon. Thank you so much for being here. My name is Parker Werns. I'm the program coordinator for the AI Institute for Societal Decision Making. And welcome to the bi-weekly seminar series for AI-SDM. Our speaker today is Dr. Paul Lehner. So Dr. Lehner is a senior principal AI and decision scientist at the MITRE Company Corporation and has directed and published on a variety of topics, including reasoning under uncertainty, AI
I
planning.
actually can do all that myself because it's in the.
Oh my gosh. Well, then I'm going to stop talking. Here he goes, Mr. Lehner. Yeah.
Thank you.
Hi, we can eat you.
I'm happy to be here and I'm sorry I interrupted your speech.
I love that. I love
Okay, so yeah, our topic today is can we accurately estimate classifier accuracy, it doesn't really matter, it's AI, without ground truth data or trustworthy expert ratings. Okay, let's see. Okay. Worked before. Parker.
Now you want me back up here.
Now I need you.
Yeah. It's weird.
Okay, we're good. Yeah, okay.
Should be fine.
All right, now we're good. So who am I? We're about to say, why am I here? Okay, so yep, I am a decision and AI scientist at an organization called MITRE. We are a nonprofit organization, but we're a really big one, like 7,000 people. We run what's called FFRDCs, Federally Funded Research and Development Centers, and if you don't know what those are, just type in NSF space FFRDC and you'll get the master list of all FFRDCs. My PhD's in mathematical psychology, back before dinosaurs wall, but back in like 1980, game ago, AlphaGo was awesome. Now I've had a diverse career. Both I did spend some time in academics, but as I'll explain in a second, it's not my thing. So I literally left. I was tenured. I literally left 1 month before starting a sabbatical. So it was just not my thing. Okay. And so I've been around various areas, game planning, AI planning, and survey reasoning, et cetera, et cetera. But the topic for today is innovation in research and test methods. Now, I'm not really an academic, like I said before. That's actually going to be important. I'm usually focused on trying to develop something to address a particular challenge. And when I do it, I usually make one effort to publish it, and either two things happen. One, it gets accepted, and the first thing I'm going to tell you today was accepted. By the way, never before presented to anybody, but accepted for publication. And the second one was not. And the other thing that happens is I drop it because I'm on to the next thing. I never get back to it. Okay. And so I think I've left lots of promising stuff on the table, which is fine for my career, but it'd be kind of a shame if it just got left on the table. So what I'm going to do today on this topic, like I said, accurately estimating accuracy without expert ratings or ground truth, is I'm going to describe some research starts in this area, with some specific, I think, intriguing results. And I'm actually hoping that somebody in this audience or listen to this podcast will say, that's kind of cool. Maybe I should, pick this up, do some research with it. And if you do, I'm at the tail end of my career, I am happy to help you do work. It's not something I'm going to do. Okay, but I'm happy to help you. Now, let's see what else do I want to say. Nope, good enough. So we're going to start off with a bit of a preamble. How much should you trust expert ratings in machine learning? Because honestly, it is often the case that when ground truth data is not available, you go to experts, you ask for their ratings on whatever it is you need to learn, and you use that as a surrogate for ground truth. Is that a reliable practice? In good practice? Let me take a step into a couple of sides. In the psychology literature, there are really two traditions on expert judgment. There's the cognitive psychology tradition, where they tend to focus on how experts think. And there's the research in what's called judgment and decision making, was it JDM and all that kind of stuff, that is much more focused on the decisions that are actually made. So they don't care how they got to the decision, they care about the decision itself. So in that literature, these folks are descriptive of an enormous amount of research. So the first one, experts aren't all that accurate. An enormous and almost unequivocal research literature implies that expert judgments are rarely impressively accurate and virtually never better than a simple mechanical judgment rule. And by that, I mean a simple linear model with maybe 5 versions. Done. Okay. If you've ever worked with expert ratings, lower and greater agreement is common. So you just have to live with that. And then you might think, well, let's just put them in the room together and they'll hash out the best answer. There's reason to think that doesn't work. If you guys are a little young to remember when crowd wisdom came out, but the crowd wisdom research basically says the worst thing you can do is let them meet. Don't let them meet. Armstrong just well, principles of forecasting, and there used to be a website called forecastingprinciples.com. I don't think it exists anymore. Armstrong was old when I knew him. That was like 10 years ago. It is a compendium of research in forecasting. You know, all the good empirical research in that space. So it's a cool place to look. It just, even looking at the book would be informative. Okay. So I will take his quote. Organizations often call on the best expert they can find to make important forecasts. They should avoid this practice. Okay. Sometimes important forecasts are made in traditional group meetings. This should also be avoided because empirical results suggest that it's not that accurate. Okay. And group meetings don't really help. Now, let's circumscribe this a little bit. In my understanding, the above results mostly applies to what you might call a judgment estimation or a forecasting task. It's really when it's a judgment call. Okay, there are a lot of tasks that I would characterize as problem-solving tasks. And let me try to explain the difference. Working on a crossword puzzle. If you have 3 people in a room working on a crossword puzzle, and somebody says, you know, 24 across 7 letters, this is the word that fits. Everybody looks at it and go, oh yeah, that fits. And they move on. Okay, that's characterized as a problem-solving task. A judgment task is when you have a partial solution like, well, I think the Iranians are going to run out of missiles and drones in about 3 days. And the next person says, no, they're going to last 2 weeks. The next person says, you have no clue what's going on. When they debate about all this stuff, that's a judgment task. It's a judgment call. And of course, almost everything you're dealing with these days are judgment calls from experts. Okay, it's not like working at crossword puzzle, but that's where those results go to belong. So I would simply have the following bottom line. For any particular application, it may be the case that your expert ratings are close to ground truth. That would be cool, but don't assume. That's just a bad idea to assume. You need to do something more to confirm it, to test it, to do whatever. And so, well, before I get there, and there are some risks if you just assume it. One, you may be surprised when you put it in an application because it may not actually work, even though you think it's great. And 2, there's actually a risk of having high accuracy results that are a complete illusion. Remember I said experts are, in many cases, can be modeled with simple linear models. Well, you know, your deep learning algorithm is going to have any trouble replicating what the simple linear model does. Okay, so it won't have any trouble replicating what the expert thinks. And that'll be true whether or not the expert's any good. So you could have a lousy model that works great against experts. And you don't know it's a lousy model. So I will tell you right now, I don't have a data set that has both ground truth and expert ratings in the same data. I look for it, but it kind of makes sense it doesn't exist because why would you go to all the expense of collecting expert ratings if you have ground truth? It's only because of something like this that you might be motivated to do it. So I can't tell you definitively this is a problem. It's going to be somewhere between a common, uncommon, or non-existent problem. I'm guessing it's more than uncommon, but less than common. But that's the first thing. I'm looking for people who are interested in doing this research. That would be part of the research you want to do. I'll talk to you about that later. Okay. So I am going to go through 3 different approaches that I've worked on to address this problem. And a bit of bonus. I'll describe the approaches when I go through them. I will tell you that first approach was published but never presented. So you're the first to hear it actually and be presenting it. The second approach was not published and never presented. So you're the first to hear it as an actual academic presentation. And the third approach is what I'm working on right now as part of the AI-SDM work. Okay. And then I'm going to give you a bit of bonus, but let's just move on. So for all 3 approaches, I'm going to jump right into giving you a numerical example to step you through it. and then tell you where it came from, and then tell you how good it is. Okay, so approach number one, we have expert ratings, and the experts just don't agree. Okay, and a little bit later, I'll tell you exactly what the practical problem was that made me invent this. So here we have 4 raters, 10 cases. We'll take number 1, raters 1 through 4 said it's C, it's D, 4 categories. It's C, and the system said it. Their classifier said it. Okay. First step, given some simplifying assumptions, which I will explain where I got those simplifying assumptions because I didn't make them up. They were derived from something we already do. That just people don't realize they're making those assumptions. But from some assumptions that people don't realize they're already making, I came up with this method, and I can estimate. Well, first of all, I can estimate the base rates. So 25% B, I guarantee you more than it's not a quarter of those that are Bs, but you have to derive that. And I can estimate expert accuracy, and here sensitivity, specificity, or whatever, it's 50% for the truth and equally probable for the rest of it. Okay, so now I have priors. I have probability that an expert will say A, if A is true, and the probability will say B, C, or D. So yeah, I can apply Bayes' rule to that. Okay, and I can come up with, from the expert ratings, a probability distribution over the correct answer for each of those 4 cases, for each of those 10 cases. Now, let's look at number 1. There's a 4% chance that A is true, according to the expert judgment. So you might look at that and say, well, if this works, then there's a 4% chance A is correct. And if you say that, you are wrong. Because the fact that the system said A is itself evidence that A is true. So about the only thing you know, given this information, is that 4% is the bottom. But yeah, but how much higher should you go? To tackle that, we need a totally different step. And here is going to be a key observation that's going to be important here and the next method. By the way, the second method is way more interesting. This will be interesting. Imagine you have a classifier that is 100%. And you have an expert who is 80% accurate. You know you have to be 80%. Unless I say otherwise, sensitivity, specificity, all that stuff is easy. Then you would expect that 100% perfect classifier to agree with that 80% accurate expert 80% of the time. Okay? Well, you can reverse that. I have an expert that I know to be 80%, and this classifier agrees with that expert 80% of the time. I can bootstrap to an estimate that that classifier is 100% accurate. That's what we're doing here. I actually think there's a typo in here, which is kind of embarrassing because I just copied this from the paper. But nevertheless, we're going to focus on, is there a, let's see, is there a button for a laser?
Yep, the red one above the arrows.
The one with the red line?
Yep. Might be really faint.
Oh, that's good enough. Okay. So across these expert answers, there are 3 cases, 1, 2, and 3, where the highest probability answer, we have no idea what ground truth is, but the highest probability answer is between 0.8 and 0.9. Okay. So of those 3 cases, the average is 0.85. Let's just take that as the average as ground truth probability. I will have a longer conversation with you if you want on what the meaning of the word probability is, but that would be way too much for this. Okay, but trust me, I've actually published on that topic, so I can talk about it. But here, turns out that in 2 out of 3 cases, the system agreed with the 0.85 answer. Okay, that would be true. You would expect 67% agreement with an 85% accurate source if the classifier is 77, 78% accurate. So from the estimate of the expert-based estimate of the probability is true, and proportion agreement with these probabilities, we can estimate accuracy for these cases at around 77%. Obviously, it's only 3 cases, it doesn't all add up easy, but you get the idea. Then we simply weight these numbers, and you come up with an overall estimate of system accuracy that's around 73%. Correct?
Doesn't the statement at the bottom
Can
assume,
you speak a little louder, please?
doesn't the statement at the bottom assume that the system and expert judgments are independent? But what if I have correlated errors?
Actually, first of all, this is only assuming one expert, okay, but you are correct. When you get to there, the simplifying assumption is, I'll just jump ahead to the next slide, but it's that the experts are independent. The experts all operate off exactly the same confusion matrix. Okay, that is not, I didn't make that up. If you take use of iterator, like kappa, and the current practice is if the iterator statistic says that kappa is too low, don't use it. If it's high, use it. Okay, under what conditions does the monotonic relationship between high iterator agreement and expected accuracy hold for sure? When can you rely on it? You have to make all those assumptions. It breaks down if you don't make all those assumptions. So this method was developed based on assumptions that are already being made in the practical use of kappa these days. But you are absolutely correct, and I'll point that to the next screen. So, yeah, I'm claiming I'm making no more assumptions that are already made, just a different method. Okay, but thank you, very good. So what we got there? Good. All right. So let's. Oh, I'm sorry. At the bottom of this is the Journal of Modern Applied Statistical Methods. That's what it was published. Sent it in. It was published. Done. Haven't thought about it since. Okay. Now, how is this method derived? Well, it's exactly what I just mentioned. I started with this kappa statistic. I, looked at the working assumption that high inter-rater agreement corresponds to higher expected accuracy of the experts. And so I said, okay, I'm a mathematical psychologist by degree. So this is a little bit telling you how a mathematical psychologist thinks. I looked at that and I said, all right, under what conditions does this monotonic relationship hold? So I derived the necessary and sufficient conditions, the proof and all the stuff's on the paper, and everything I just said is what it does. And then I used those assumptions to basically derive a method on the previous page. Okay, cool. And then as a scientist, I tested the heck out of this problem. And that's gonna be a fun story. Okay, moving on. So, does it work? So, these are just pictures from the paper. When those assumptions are satisfied, it works great. This is all simulation results. We had 3 simulated experts at 60% accuracy. Part of what I'm interested in is I don't want your estimate of the accuracy of the AI classifier to be limited by the accuracy of the experts being used to evaluate. That's actually part of what got me started here. So here, with our simulated 60% accurate experts, the simulated classifier, let's say, is 90% accurate. Using the system I just described, the estimate of accuracy is around 90%. When the system is 30% accurate, the estimated accuracy is around 30%. It works great. It works pretty well when you end up 50 in your sample size. Okay. But that's when the assumptions were satisfied. That's fine, but in reality, they're never satisfied. So I try to break it. Honestly, I really try hard to break it. So I messed with the I messed with the independence of the experts. I messed with the equal accuracy, which is also an implicit requirement. I just did everything I can to mess it up, break up all the assumptions. And what you ended up with was essentially regression to the mean. When the best answer, the true answer is 90%, it tended to come up with 80%. When the true answer is 30%, actually it was pretty far off, but when the true answer is 10%, it came up with something that's too high. Okay, so basically it just regressed it where it could be fit. Now, that's actually good, because if you are building an estimate of the accuracy of the system out of what essentially is nothing and no ground truth, you'd like to be confident that it's a conservative estimate. And in practice, that's what it turned out to be. Okay, so cool. Even when the assumptions are violated, and the paper gives some explanation for why it worked this way, but even when the assumptions are violated, it was actually, in my opinion, better. All right, but yeah, okay. But does it really work? So, actually, before I do that, I'll just point out, it was used. And however they used it, but I know the IARPA, Intelligence Advanced Research Project Activity, which I got a fair amount of contact with. There was a program called FUSE, and it was about AI reading of scientific literature to anticipate emerging technologies. You know, what's gonna be the next, best, the next greatest thing? Give me a second. So when they tried to come up with a ground truth data set, either for learning or for testing, what they did is they would pick an area. I remember genetic algorithms was one of them. And they would go to the luminaries in the field. I think John Allen was dead by that point, but they went to people like that in the field. And they said, when did this emerge? And they gave, here's the description of what we mean by emergent. When did this emerge? One person would say, yeah, it was really big by 1985. Next person would say, you know, it really didn't come out seriously emerge until like 2000. Next one would say 2005. It was all over the map. And these are all people working together in the same field. You did not have pioneer agreement, that they were stuck. I mean, this was literally a case where somebody walked into my office and said, what do I do with this? And that's where it's meant. They also use it on something called FungiCat, which is a capability designed to detect and assess the risk of DNA sequences that never before seen. Well, never before seen means no ground truth. You need extra judgment for testing. They had no choice but to do something like this. But cool. But does it really work? It just seemed to be too good to be true. Okay. And as a scientist, you don't believe it. It's too good to be true, even if I had what I thought was good evidence. So I ended up spending 4 years at ARPA on loans with government, and I was their chief for test and evaluation. So I had money, so I could hire Lincoln Labs to break it. I said, okay, just do what you. And that was literally their instruction: break it, and if you break it, try to make it better if you can. And it worked okay. They tested it. I mean, it worked okay, but it didn't work as well as the simulation results suggested it should. So, you know, well, is it good or isn't it good? And after a couple of years working on it, I asked the project lead, okay, tell me, what do you think? And he goes, man, I don't know. I still think there's something wrong with this. And that was my same feeling. So I never really promoted it. And I found the flaw. And I will tell you later because I tried to use it for something else and the flaw emerged. And I'll tell you later. But if anybody's interested, never published the flaw, so there's a rebuttal paper waiting to be written. I'm happy to help you. And if you want to take it further, like the problem may be fixable, I'm certainly happy to help you if you want to tackle that. Okay, anyone interested? We'll leave that for you. Okay, so let us go to number 2. There's a Google Share folder that this was not published. But I did write a paper, I did my 10, I then forgot about it. So both the paper that describes what I'm going to show you and the Excel spreadsheet that lets you do every calculation I just did, is there's a second document. So everything I say here is completely replicatable by you guys. Anybody who wants. Okay. So we got a model and it predicts an output value. We call it output 0.9, 0.1, 0.2, 0.8. And when you want to test it, you test it against ground truth and you go, oh, 0.9 is true. So it's all 0.1, 0.1 false, 0.2 false, 0.8 true. That one seems to work pretty well. So you test the model against ground truth output and you get something that looks like this, an ROC curve. Okay, cool. Now, what happens if you don't have ground truth? And in this case, I don't have expert ratings either. I'm literally saying you don't need no sticking expert. Okay, so anybody remembers Cheech and Chong? That's what that came from. Never mind. Okay, I'm old. So, but let's suppose what you have instead is a variable like a medical test, where the value that it comes up with, whether you test positive or not, whether it exceeds threshold or not, is dependent only on ground truth and not on the model predictions, the conditionally independent variable. Okay, so you got that. And here, the example I'm using is sensitivity 0.6. So just to repeat, it's conditionally independent because if the model predicts 0.9 chance that it's true, there's a 60% chance the test's going to flag true. If the model predicted 0.001 chance it's true, but it happens to be true, there's still a 60% chance it's going to flag true. Okay, that's what we mean by conditional independence. Okay, so if I call it a CI variable, but wait, I'm gonna mess it up. Okay, I'm gonna randomly flip 26% of the falses. It's true. Okay, totally messed it up. And that random flip is not dependent on ground truth. So just as an illustration, here's false, it's correctly false, it stays false. Here, it's true, but as far as the test is concerned, it's missed positive, and that stays false. Okay, so it's a random flip only on the readings, and in no way related to ground truth. But this 26% flip, I can derive from just these two numbers, and it gets me a conditionally independent variable that is symmetrically sensitivity and specificity. That's the key thing. Okay. Then, well, let's take that model, that CI variable with 70% accuracy, and test it against this model. And you end up, and then apply some equations that are in the paper and in the Excel spreadsheets, which you can replicate, and you end up with an estimated ROC curve that looks like that. Hard to tell. Okay. Well, that's a fairly robust phenomenon. Once again, I tried to break it, so I changed lots of parameters. I'm sure you can think of more. I can tell you that's not in the paper, is that here I made the base rate 0.1, and then positive and negative cases had a very different distribution. Yeah.
Well, maybe I missed this, but isn't the variable essentially playing the role of an expert?
Sorry, say it again.
Isn't that variable playing the role of an expert here?
You can think of that variable as playing the role of an expert. Yes.
So you don't need access to that.
Well, to make this work, you need a conditionally independent variable where you know sensitivity and specificity. That's what you need to have happen, like a medical test. Okay. Now, experts are not conditionally independent. Okay. They will look at the same variables that the model looks at. So it's not really playing the role of experts. It's something very different. Okay. But you can see, and it worked pretty well. I could just tell you that, as I recall, it's been a while. If I push the priors or the base rate down to like 0.05, 0.03, so it's really, really low, it tends to fall apart. But in these ranges, priors at a 0.1, sensitivity and specificity 0.95, 0.6, anything in that broad range, it seems to work really well. Okay. So, if somebody's interested in picking this up, here's what I know and don't know. You can, first of all, if you want to do it, you got to independently replicate it, which I guarantee you is no problem. It's literally nothing but algebra. I can tell you the experience. It was one of these cases where there were like 5 variables and 4 equations. And I spent like months and months trying to come up. There's got to be one more equation that connects these two things. And when you read the paper, I think I call it an R factor. And it took me forever to come up with it, but that's it. When I came up with the last equation, everything was derived. Okay. Now, what I don't know is robustness. No clue. I mean, I said 60% and 95% sensitivity and specificity. Suppose I assume that, and the actual sensitivity is 0.63. Does it fall apart in the estimation, or is that just lead to a minor error? Right? In order for this to be useful, you got to figure that out. Okay, so stuff like that's what you can do. Now, it would be nice if I could have applied this to an actual data set that had both the predictor variables and a CI variable, like a medical test. And you would have thought, like, the all the Kaggle stuff, couldn't find them. But if you had that, somebody should talk to NIH. Be really cool. And actually, if it were me, I think the most interesting application of something like this is, suppose you have a medical test, let's say an early COVID test, and you come up with a new medical test that you think is better, and you want to get a quick estimate of how accurate it is. You can bootstrap the results of the old test to estimate the accuracy of the new test before you can get any ground truth data. That'd be cool. Okay. Let me get an NIH connection, that'd be kind of cool. Okay. So let's see. Oh, yeah, but wait, there's more. For those of you who remember those old commercials, but wait, there's more. Yeah, I am old. You might think, well, if you can test the accuracy of a classifier with a CI variable, can you actually learn a classifier from a CI variable? Seems plausible, and in fact, you can. So let me explain what you're looking at here. This is my bonus slide. So this is a logistic regression applied to, learning a model based on some number of predictive variables that I tried to make messy. So it's learned against ground truth and it's tested against a different ground truth data set. Okay? You see it gets 98% accuracy. Oh, sorry, I'm saying that. AUC of 0.98. This is a model that was learned against a symmetric CI variable that had a 20% error rate. But when it's tested against ground truth, it gets about 98% accuracy. Okay, sorry, 98% AUC. Photo perceptrons, similar. Sorry, I'm not a machine learning guy, so somebody had to teach me how to use Weka, and so this is what I got by using it. But it didn't matter which method you used. Some of them worked great, some of them worked lousy. If it worked great with ground truth, it worked pretty much equally great with the 20% error-prone variable. And if it worked terrible with ground truth, it worked terrible. This got to be an error in the coding with the CI variable. So cool, says you can do that. But wait, there's more. Sorry. Let's break this down a little bit. So this is this one here. The classifier learned from ground truth and tested against ground truth. It's a different run. AUC is about 0.98. Proportion agreement with ground truth is around 92%. So AUC tends to be higher than the proportion agreement. So when ground truth is true, there's 92% chance that we'll say it's true. Okay, or it's false, whatever. This is this thing here. So the variable was learned. Sorry, the classifier was learned against this 20% error rate CI variable. When tested against ground truth, as you can see here, it's almost as accurate in that particular run. By the way, I just picked these two because I ran fast. No, there's nothing special about those. But interestingly, when you learn the classifier against the CI variable and you tested it against that CI variable, okay, just test set, it couldn't work. It could not come up with an agreement. It's an 80% accurate variable, and it couldn't get more than 75% agreement, no matter how hard the thing tried to learn. So it only agrees 75% of the time with the variable it's learning from, yet it agrees 90% of the time with ground truth. How the heck does that happen? And the answer is, right? Remember I said before, if you have an 80% variable and the classifier agrees with it 80% of the time, it's evidence it's 100% accurate. Well, here we have an 80% variable. The classifier agreed with it 75% of the time. And from there, you can estimate before you see any ground truth that it's going to be about 91 to 92% accurate. Wasn't too far off. Okay. So go ahead.
Can you explain again how you derive the CI label?
The CI label is conditionally independent. In this case, I simply took ground truth and I started with, okay, I'm going to create the CI variable. 6% of the cases where it's true, I'm going to say true. 40% I'll say false. Just randomly.
So you're running a small compliant with CI label?
Sorry, again.
So CI label generation is randomized.
Yes. Yes. Randomized relative to ground truth. It is conditionally dependent on ground truth. So if sensitivity is 60%, if ground truth is true, 0.6 chance randomly it'll say true. If its specificity was 95%, if it says false, 95% chance it'll say false. But other than that, it was random. Okay. Like I said, like a method. But here we have, back up. So yeah, it's the comparison of this number, the 80% accuracy, to the proportion agreement that the classifier could come up with that variable that you use as the basis for estimating the accuracy of that classifier, like basically, in part what I did before. Okay, and you can see the same thing work with voted perceptrons. Like I said, these are in fast. You can pick any of these. You'll see the same basic pattern. Okay, so you could argue that what's cool about ground truth is that it's a 100% symmetrically accurate variable. And it's not the 100% that's important, it's the symmetry on sensitivity and specificity. And you can make that argument. And if you want to extend that argument, you can say, okay, well, this is nice, the 80%, but come on, What's gonna happen when you push that down to 55%? So you have a 45% error rate in your variable. And that's this. And as you can see, the classifier that is learned from a variable that has 45% symmetric error isn't quite as good. But it's not bad. Okay, it's 85% accurate. Learning from something that's got a 45% error rate. It couldn't, the CI classifier couldn't replicate the CI variable. Just couldn't do it. Okay, they came up with that, and it's the comparison of this and this, which gets you that basically 80% estimate of how accurate it'll be if you never look at ground truth. It's not as good as when it's higher. So that's cool stuff here. Okay. Okay. Oh yeah. I put that in so I wouldn't forget to tell you. Now I can tell you what was wrong in my first perch. I was trying to break it by messing with the error rates of the experts. Okay. And what I accidentally created was a ground truth variable that was conditionally independent of the experts, okay, with symmetric error. And so I created exactly the situation. And the fact that no matter how much I pushed down the error rates or the accuracy of the expert didn't have much effect, that's why. Okay, so that was what I did wrong in the first one. That was the flaw I didn't discover. Okay, it never occurred to me it was to structure the relationship and not the error rates in the experts. That was important. Okay. I'm gonna go work on number 3 first, but any questions on that while I take myself a sip?
And this, how do you know the export accuracy or the CI variable label?
Well, here is all simulated. Okay.
Yes, but. In an application.
If you have an application, I would look for something like a medical test, okay, which is supposed to be.
So it is something that's validated against the ground truth and stuff.
Oh, yeah, yeah. A typical medical test, you know, you have sensitivity and specificity with respect to ground truth. And so you start from there. Now, it may be that medical tests are not completely independent of the forecast. A patient, I don't know, okay, but that's the structure I think. And if you're, and this is kind of this part before, if you're close, does that mean you're still gonna get a close answer or is it gonna fall apart? That's really an empirical question. I don't know the answer. But in terms of being able to do this in theory, it's gonna work. I just don't know if it's gonna work well in practice because I don't know the extent to which input loss leads to output loss. Yes.
We had a lot of data sets with ground truth to get the CI test, medical test. Then meta learning also applies, right? Like you could be learning on the tasks with ground truth and then extrapolate to this new task without ground truth.
Yeah, I actually related to that, see if it's the same thing. I was actually thinking that if you have a small ground truth data set, okay, and you might take a predictor variable, and I've actually tried to do this, but I didn't have any money to do this, so I just stopped. That has the lowest correlation with the other variables, but is conditionally dependent on ground truth, and use that as a surrogate CI variable. And then you use up your ground truth to figure out what the CI variable should be, and then you learn from the CI variable. And so I may have 100 cases of ground truth, but I can, you know, I might have many, many more cases with the data without ground truth. So something like that. I mean, things along those lines, I think, are feasible.
Or you need only one task, get the conclusion matrix of the CI variable, right? You don't need many tasks.
Yeah, we just need the one variable. One test.
It's like 100 ground truth samples is enough, right?
I actually don't know the extent to which what I just described depends on that. It's a good question. Now you're thinking like I want you to think. Please, I'd be happy to help you. Okay, this third method is what I'm working on now as part of my contribution to AI-SDM. Okay, and we got 2 things to start with. We have a model that was learned and tested against expert ratings. And we have some notion of how accurate the experts are. And you want to combine those 2 things to come up with an estimate of how accurate the AI is, the classifier is. Okay. I'll use the example on the emergency response. So you had a presentation, I think not too long ago, from what's that last name? Starts with M.
Manzini.
Manzini, thank you. And he was talking about, automated interpretation of building damage assessment after, like a hurricane, from drone imagery. So the idea is, if you can take a snapshot, quickly determine that this building was destroyed, you can get help there fast. You can save people's lives by sending first responders where they need to be. Okay, cool. But experts aren't perfect in making those kinds of assessments. There actually is some limit to how much they know, but let's assume for the moment that we know how accurate they are. The emergency managers, and the model doesn't agree with the emergency managers all the time. So in reality, when you use that to, send first responders to, save lives, how often are they going to send it to the right place? Okay, so that's the kind of thing we're interested in. Something about the expert accuracy, and you have data on how much they agree with the expert. Let's see. All right, good enough. All right, all I can do here is go right to this display in the spreadsheet that is definitely in progress. But I'll give you a couple of interesting observations. This is binary. Okay. So in order to estimate the accuracy of the AI, I need a few things. I need to know, how good are the experts? So here they're symmetrically 90% accurate. By the way, I did not make the symmetric mistake again. Don't worry about that. Second, the extent to which the AI agrees with the experts. So there's 90% agreement with the experts. I need to know base rate, how many cases the experts assign, let's say true, false here. What proportion of the test cases the experts say were true instances? Okay, and I need to know something called complementarity. To what extent do you think experts in AI, can they come up, holding everything else constant, they come up with the same answers or different answers? Okay. In the drone imagery case, in a lot of cases, the model was learned from the expert, so complementarity is pretty much set zero, because it's designed to mimic the expert. In other cases, I'll show you the effect in a second, it can be much higher if the AI is learned from something else. Okay, now, given these settings, it's a calculation. You learn two things. One, even though the experts said 30% of the cases are true, the best estimate of the portion of cases in the data set that are true was 25%. Okay, because there is error in the expert judgments, because there are more falses in their judgment than truths. Okay, the preponderance errors are going to be in the false side, so the correct calculation was 25%. Now, the estimate of the AI accuracy here is 78% sensitivity and 81% specificity. Now, you might look at that, but wait a minute, that's symmetric. That's symmetric. Why the heck isn't that symmetric? Okay. And I can tell you, if they said 50-50 ground truth cases, positive versus negative, this would be symmetric. If they said 70%, these would be reversed. And so that lets you conclude, while sensitivity and specificity are in fact independent of base rates, estimates of sensitivity and specificity, when you fold in the fact that you're learning from experts and they have error, are no longer independent of base rates. ROC curves may not apply. That's kind of messy. And I haven't got anything beyond that to say on that, other than the assumption you learned your entire career may not hold true. Okay, now, I'm not just interested in whether the AI is right. I'm actually much more interested in whether the combination of an AI and user is right. That's the AI-SDM thing. And so for that, I need more information. And the most important thing here is what I call discrimination. When the AI says A and the user would have said B, and the AI is right, what are the chances the user's going to say, yeah, I'll go with the IA versus I'll go with my original answer? And reverse, when they're right and the AI is wrong, what are the chances they're going to go with the right answer? So discrimination is the odds of going with the right answer when they do or would have disagreed. I say would have, because a lot of times they don't solve it separately. But conceptually, they would have disagreed, counterfactually. Okay, once you fold that in, then you can calculate the accuracy of the combination. And very importantly, for the AI-SDM work that I'm involved in, you really want to calculate what we call counterfactual distance. Let me explain that real quick. Let's do the building damage version of this. The building is destroyed. You need to send help right away. The emergency manager, sorry, the labeling is all off. The emergency manager, the expert, if they were left on their own, would have looked at that image and go, yep, building's destroyed, send help. But the AI convinced them otherwise. And so they said, no, building's fine, go send help somewhere else. That's a rare case. We can calculate how rare that case is given this kind of data. Okay, but that's a really expensive rare case. Because that's a case where you end up with headlines, AI leaves people to die. If they hadn't used that AI, these people would still be alive. And that's a very expensive case for the ongoing usability, utility, acceptance of an AI capability. So we want to calculate that as well. And given the stuff I just showed you, we can. Okay. Now, just the only thing I changed here is complementary, the extent to which they disagree. That is literally the highest number I can, consistent with the constraints I have up here. And as you can see, you get a very different answer on estimate of AI sensitivity specificity. You no longer still know this metric, and combined accuracy goes up. So you can actually get accuracy that's better than either alone. And in various ways, it always comes out to the extent to which they would disagree. The key to getting better accuracy out of the combination of an AI and user is the extent to which they disagree and getting the right answer when they do disagree. Okay. All right. Real quickly, how do we use this? So in the AI-SDM work, I talk about something called a use pattern. How you use an AI has a real big impact, not only on the value, but also on the acceptability for the people and the stakeholders. And then for the stuff that Tom showed, there are different applications and there are different ways to use it. We're just going to pick this one right here. And the idea is use the AI to prioritize the imagery to show the ones that are most likely to be battle damaged, destroyed, to the emergency managers. And then they look at it, they look at the AI explanation and they decide. Okay. Let's get past this one. Using that, throwing a couple of utilities here, the gist of it is that when you use this AI prioritization, you get there faster. If you normally get a score of 5 for the current process, you get bonus points for getting an answer and getting the first responders there faster. When you fold that into your calculation, here's the outcome matrix, outcome matrix in both cases. In fact, you'll see that without the AI, they're a little bit more accurate, but nevertheless, the value of getting there faster clearly outweighs the small drop in accuracy. Okay. Nevertheless, there's this other thing. This is the case where the building's destroyed. The experts would have said destroyed if they didn't use the AI, but they used it. That gets a real negative value because that's that PR nightmare. But that happens rarely per our calculation. So when you fold that into the calculation, it has very little effect. That's in this domain. In another domain like AI image reading of cancer, it's a much bigger effect, much more probable. Okay. Note this. So that's basically it. I'll tell you what you should do next. If anybody's interested. So first thing is don't treat expert ratings as reliable surrogate for ground truth. Just don't. Be suspicious. Find ways to estimate true accuracy when classifiers are learned from expert rating. If you have a separate data set with ground truth and you learn from the experts, then that's perfectly good to test it without any of this fancy stuff. But if you don't have that, I think what you need is to find or construct some data sets that have all these elements. You have your predictor variables, you have your expert ratings that are based only on the predictor variables, you have your CI variable, and you have ground truth. COVID predictor factors. Expert assessment as to whether or not a person has COVID based on their symptoms. Medical test results for COVID. Did they actually have COVID in retrospect? Okay. I mean, you can construct that kind of information. It's got to be there somewhere. And if somebody could find it, you could study all of this stuff in a very straightforward fashion, both with theoretical and empirical stuff, using that kind of data set. And that's, I think, what you really need to do to make progress. And if you did, I think you have an opportunity to substantially impact the vector of machine learning research. Okay. And if you're interested, I would be happy to help you in your research endeavor. As far as I'm concerned, I'm done. That's it.